So far, we've focused on one random variable at a time, and in this video, we'll start to look at what are called joint distributions, where we have two random variables that might be related to one another in some way, okay? And this can be extended to more than two random variables, but we'll just stick to two for the slides here. So here are some examples. We could look at the relationship between, mother's education and children's education, and those would be two discrete random variables. We expect there to be some positive association between those two variables. Similar for the second example, rates of investment and economic growth in macroeconomies. That would be two continuous random variables. Again, we would be expecting some positive association there. We could also think about, in labor economics, how income distributions or wealth distributions or something like that differ by race. Race here would be, if we sort of numerically coded it, a discrete variable, and income or wealth would be treated as a continuous distribution. So you can look at joint distributions, where one is continuous, one is discrete, something like that. The theoretical treatment is definitely easiest, I think, for the case of two discrete variables, and that's what we'll focus on in these slides. We'll look at the first sort of few topics here in this middle section in this video, starting with the idea of a joint PMF. And a joint PMF is going to describe probabilities associated with like combinations of x and y values. So it would describe, what's the probability x is equal to 2 and y is equal to 3, for example. Okay, this is a formal definition. We're using this lowercase f notation that you're familiar with from PMFs for discrete variables. And if we say, little f of x comma y here, we're saying the probability, because this is a joint PMF, so it's a probability mass function. Remember, x and y are both discrete. So there could be some positive probability that x is equal to whatever this value is, and random variable y is equal to whatever this value is. Okay. So this is sort of an intersection type probability. X is equal to 2 and y is equal to 3, for example. All right. And in general, if we want to find the probability that x and y are in any set A of pairs of x, y values, we just add up the joint PMF values for all of the, x, y pairs that are in that set. All right. That'll make more sense when you see an example in a moment. The joint distribution, if you have the whole joint distribution of x and y, you can use that to sort of back out or recover the distribution just of x or the distribution just of y. And in this context, those are called marginal distributions. Right? The first thing I want you to know is a marginal distribution is not a new concept. It's just the distribution of a single random variable. It's what we've been studying so far. But now, if we start from a joint distribution, we have two variables potentially. Let's call them x and y. And so x has a distribution and y has a distribution. And particularly to distinguish those separate distributions from the joint distribution, we might call those marginal distributions. In general, the idea is if you wanted to know, for example, the probability that x is equal to 2, and what you had was information about the probability that x is equal to 2 and y is 1, x is 2 and y is 2, x is 2 and y is 3, etc. What you would do is you would just add up all those joint PMF values across all the possible values of y. All right, so that's how you would recover the marginal distribution from the joint distribution. Now, often we're looking at x and y because we have a maybe strong hypothesis that they're related to one another in some way, but it could be that x and y are independent, and they're independent if their joint and marginal PMFs follow this expression right here. Notice the subscripts here on the marginal distributions. We haven't been using those so far because we've only been dealing with one random variable at a time. But now we have two random variables, so if we write little f of 3, you don't know which variable we're talking about. Is it x or is it y? So we subscript it to be explicit about what variable we're talking about. Okay. This expression says the joint PMF is just the product of the marginal PMFs. If x and y are independent, then that expression will hold. And if you think about what that means in terms of the underlying probabilities, you'll realize it's just the definition of independent events that we know well from our study of probability. So the joint PMF for discrete random variables, remember that little f of x comma y is exactly that probability. X is equal to little x and y is equal to little y. And then what are these marginal PMF values? Well, the first one is the probability x is equal to some particular value, and the second one, y is equal to whatever particular value little y is in here, okay? And so if you think of this as one event, and this is another event, and this is the intersection, again, it's exactly the idea of independent events. It's not really a new concept. Okay, let me show you a joint distribution, just to give you a numeric example to think about here. We'll do some of the questions here in class, but I'll just introduce the idea and maybe do one of the examples here. So this is the joint distribution of levels of education in a large sample, about 400,000 of opposite-sex married couples observed in 2022 in the U.S. And so just to keep things tractable, I've categorized education for husband and for wife as being in one of three categories: high school or less, some college, and college grad or higher. Okay. And the wife's education we're going to call variable x, husband's education is y, and technically random variables have to be real valued, remember? So we can accomplish that here just by giving each education category a number, 1, 2, or 3, right? So these 9 values right here, these are joint PMF values, okay? Each of these shows the idea that if you pulled a couple at random from this large sample, which maybe we could just treat here as a pretty close approximation to the population of opposite-sex married couples, what we're saying is if you pull a couple at random from this population, there's about a 10% chance that the wife would have a college degree and the husband would have some college education but not a college degree. Okay? These probabilities, up to rounding at least, have to add to 1, just like any valid probability distribution. All right? We're asked here in the first example, what fraction of wives have a college degree? So what we're being asked to find in terms of random variable x is the probability x is equal to 3, because 3 is the code that corresponds to having a college degree. And this is an example of a marginal probability, because we want to know the probability of something about x alone, not having to do with how it's like associated with y, okay? And so what we really need to do is just add up these 3 values. 0.06, 0.10, 0.31 will give us 0.47 is the total. So this is the share of wives that have a college degree, or put differently, if you picked a couple at random, what's the probability that the wife would have a college degree? Almost half. Okay. If you're trying to put this together with the notation, the more formal notation on a previous slide, what I would say is, all right, this is again, a marginal probability, a marginal PMF value, f sub x of 3. And the way we find it is we add up the probabilities that x is equal to 3 along with different values of y, and we add it across the different values of random variable y that can occur. So after summing all of those joint probabilities, we get sort of a total probability that x is equal to 3. Okay, so let me just move this over just to be a little more explicit about it. So we have 3, 1 is x is 3, y is 1, right? That's the 0.06. Similarly, 3, 2 and 3, 3 are referring to xy pairs there. So that's what it means to sort of add up across the possible values of y there. All right, so that's an introduction to joint distributions.